This will be the last example in establishing continuity of a function at a certain point C, using the definition itself. So here we are going to show that the function f of x is equal to x at every point of C element of real numbers, meaning and on all possible values of real number. So basically, the first example was with exact value of C. This time it's we've been doing general forms or a lot of numbers, but a lot of possible values of C. But that's the point of also continuity. We can also check the continuity at all points of C possible of C. Now to do this, sorry, this is not x, absolute value of x, my bad. So we are going to use here a definition, and I'm going to write here the portions of the definition that will be involved in the process. So actually the definition itself is let a certain set A is a subset of real numbers, and F maps from A to a set of real numbers, and there exists C. That's part of the definition, okay? Then we can say that F is continuous at C if for every epsilon greater than 0, there exists delta greater than 0 such that if x is a point in A or x element of A satisfying this the distance of x and C is less than said delta, then we need to show this inequality. If we can, that less than epsilon, definitely we can now say that our function is continuous at every point in C. And again, we will just be sticking with C itself so that our f of C is just the absolute value of C itself. Okay, so sorry, that's C, because we don't have the exact value for C. So we'll be doing this, but of course part of that is to identify a certain delta greater than 0. We need to find or express delta in terms of a certain expression or exact number if we can, before we can proceed with the proof. To do that, my suggestion is of course always start with the scratch work so that we would know the correct expressions to be used. This is our target, working backwards, and then we can actually by substituting the necessary functions here, our goal is to come up with this form. Okay, x minus c, because once we could have the absolute value of x minus c, which is according to the definition less than delta, we can now write a certain expression for delta. Okay, so anyway, let's continue this. I believe this would be very short because we will have absolute value only of x. So you have here absolute value of x minus absolute value of c. This is still less than epsilon. Take note, you would like this, not this form, but there is an important, okay, take note of this. Also be reminded of the properties of absolute values, because there is a property of absolute value which tells us that the absolute value of the difference of two absolute value quantities is less than or equal to the difference of the quantities themselves. This is part of our discussion before, and we have a property for this. This tells us, and from this we are very lucky that this already appeared. This is our goal. That's why I mentioned earlier that this might be very short, since this is still less than epsilon. Okay, this is still less than epsilon as indicated here. That would mean x minus c is less than epsilon. What would be now our delta? If this is our goal, or this is to be satisfied, and this is our expression here, it is clear to say that our delta is just epsilon itself, because once we change this to the epsilon, this is its form. So unlike the previous examples where we had a lot of possibilities for our delta and even pick two out possible and a minimum of the two, here just simply epsilon. Okay, so once we are done with this showing that epsilon is really existing, delta is existing, which is epsilon, and we have here for every epsilon, that would mean we can start with our proof. Let epsilon be greater than 0, and then we are going to have our assumption delta is equal to epsilon. So we have met this part, then definitely we're going to proceed this here. Then if the absolute value of x minus c is less than delta, okay, which is also our epsilon, take note of that. Okay, you can also write it like this if you would like to, but other references would not write that, because our goal is this. The purpose of the scratch work is that you will be guided on the process. And since we are done with that, let's continue. F of x minus f of c, which is equal to the absolute value of the difference of the two absolute value notations. This is c. Okay, which we're able to emphasize to be less than with this. This is also the purpose of the scratch work, which is less than x minus c. Less than equal rather, according to the property of absolute value. Let me change this. This is not 0, okay? This is just equal, this is just c. Then this is less than epsilon. As you can see here, you have this less than epsilon. Hence, we have reached our target. Okay? And with that, simply making statements, hence, the absolute value of f of x minus absolute value of f of c is less than epsilon. Since epsilon is greater than 0 is arbitrary, then we conclude that, okay, this one here, this item, f of x is equal to, which is equal to absolute value of x, is continuous. At, you will have, not at every, yes, at every point C element of R. Okay. I mentioned that this would be the last example, but last example without trigonometric functions, because we are to share as well later in the next two videos proving continuity for sine x and cos sine x. We'll have that in a separate video, but for this, thank you very much for watching.